Okay. Yeah, okay. I'd like to thank the organizers for giving me the opportunity to say something about the algebraic aspects of the AdS CFT S matrix. So, well, I will first tell you in what model I'm working in, then tell you something about the full quantum symmetries, the Hopf algebras, and finally about Lie bialgebras, which are kind of classical structures, algebraic structures, where we found some nice expressions for the R matrix. So the setup is still large and large charge AdS CFT. So if you want still the spin chain picture, even though spin chains were, I think, already declared dead at the last conference, but somehow they are still alive. Lots of people still do computations there, so it's still worth it's still worth to really get some nice understanding of what's going on there. So yeah, I will deal with spin chains, long range spin chains, symmetric under PSU 2,2/4, and usually infinitely long spin chains. So I insert infinitely many vacuum states, complex scalar fields, and as we all know, in this process of choosing this vacuum, we have this residual symmetry algebra, 2 copies of PSU 2/2, and this product structure enables us to work with 1 copy. So that's basically the setup. We will study the S matrix and algebra behind with this symmetry or its central extension. And yeah, the spins, of course, of the spin chain, the excitations transform then in the fundamental representation of one of those copies of the algebra. So just to fix the notation, so this PSU 2/2 consists of 2 SU2s, which we call R and L, and 8 superchargers, Q and S, which transform under the spin 1/2 under the appropriate SU2s. So this is meant by those indices. And so quite important about this algebra is, even though this is a simple Lie superalgebra, it's the only one which allows for a universal central extension by 3 central charges, CPK. There are no other such simple Lie superalgebras, and I think this is one of the reasons why our model is quite special. So those central charges arise, well, if you say commute to say a positive root with a negative fermionic root, you get this one central charge C, which has a role of the Hamiltonian in this model, or the energy eigenvalue. So this happens for all PSU n/n's, but those other 2 central charges, they just appear for PSU 2/2. And this makes it quite special also for physics, because Nicholas first used that. He identified those central charges on the fundamental representation with the appropriate Magnon momenta. So this special central extension, this special mathematical feature, allows us to do physics, actually. So the fundamental representation looks as follows. So you have a 4-dimensional space spanned by 2 bosons, 2 fermions. And so these are, of course, momentum eigenstates when you think of the original spin chain with the infinitely many Z fields. So, and as was also shown by Nicholas, is that some of those generators, the bosons basically act canonically on the spin chain, but the fermions change the length of the spin chain, so create or annihilate vacuum fields, or in this strange basis, it's well, half vacuum fields, but this is the basis appropriate for the algebraic, to study the algebra behind.
Why by dimension?
So it's, if you want just a basis change, you can start with real z's, I mean integer values, but then you say rescale one of the phi's or one of the psi's by square root. Formally, it's if you want, it's purely formally, but this is a basis which is nice for the Hopf algebra picture. So you don't need that, but it's...
I saw that E and C are central elements, and I think that E acting on chi is AB, Z chi.
Yeah.
Chi is a different vector.
Yes, so the point is that here we are just working on one fundamental representation, and I said we are working with infinitely long chains, so this Z has no effect here whatsoever, yeah?
Just delete it.
I could just delete it, but the point is I want to explain you how Hopf algebras come about in this picture, and this happens for the tensor product of two fundamental representations. So then the Z really matters. But here it doesn't matter, so this is really central. I mean, it acts centrally here. The commutation relations are central, but the co-commutation relations, which I will explain on the next slide, they get modified. But it's still a central element.
But I'm used to, to the situation when you have an iterator acting in one definite space, vector space.
Okay. Here on this picture, as I said, you can't forget about it. If you think of this whole picture, it's different, yeah, on the full spin chain. But if you just think of PSU 2/2 centrally extended and this four-dimensional, finite-dimensional vector space, there it's central, yeah. But if you think of those finite-dimensional vector space as, in fact, an infinitely long spin chain, then it's a different representation. And then I don't claim that those are central. Then they behave differently. Okay, so.
And does this square root of Z obey Fermi statistics?
Well, there's something which formally looks like that, but in fact not. No, it's still, I mean, bosonic. Okay, so as I said, on the one fundamental representation it doesn't matter, but there's a different Hopf algebra picture. Hopf algebras basically tell you how to act on tensor products of representations via a coproduct. So usually physicists don't worry too much about that because usually Lie algebra generators just act on each tensor product individually. But it turns out due to this extra Z fields, which appears for the fermions and for those extra central charges, you need to modify the coproduct, the way how it acts on tensor products, in the following fashion by introducing a formal operator u and u to the -1, which basically just gives you e to the momentum of the appropriate excitation. Yeah, so it's a slight modification. So it's not an ordinary Lie algebra, but a Hopf algebra. So, and also how to derive the S matrix is by computing the invariance equation actually with a coproduct. And so this actually enables you to fix this S matrix completely just by Lie algebra, by using the Lie algebra, which is quite unusual, but you have this modification, this extra u. Yeah, and by the way, the Hopf algebra picture also allows you to get constraint between p, k, and u, because all those central charges need to act symmetric on the tensor product.
But this is the usual algebra, right?
This is, I mean, we are talking about the usual.
The algebra centrally exchanged, but it's not deformed.
By deformed,
Extended.
it's centrally extended, and by twisted or yeah, in this context, I just mean the co-algebra structure. So the algebra is still the same, but the co-algebra gets modified.
Is it equivalent in some sense to the old co-algebra, or is it essentially different co-algebra?
Well, it's the point is it's a twist deformation. Some think of that as kind of gauge, but it's really essential here to get the S matrix. So it's not the same. I mean, you have this extra u generators here and u to the -1. So it's essentially a different co-algebra.
Maybe you could achieve this by change of bases.
Yeah, but this comes about at using, say, non-local labels for the eigenvalues of the central charges or something. So in some sense, they're equivalent notations, but, well, yeah.
You don't have to use this non-trivial coproduct. You can just think about the algebra, the Lie algebra, as the Lie algebra with a standard coproduct.
Yes, you can think, and then
What's
you
wrong with this picture then?
nothing. There's nothing wrong with
Why
this.
should I introduce all this use, all this non-trivial coproduct? Let's just use the simplest possible coproduct.
Well, you can, but you have a non-trivial coproduct anyway when you introduce Yangians. So, what's the problem with this picture? I mean, it's a nice algebraic framework, so, and everything comes out automatically. So, you don't have to use it, but you need a non-trivial coproduct anyway, so better start thinking about Hopf algebras if you want it or not.
So you don't need the Yangian to
Yeah, but okay. But the Yangian is there anyway, so if you like it or not. So yeah, so even though the S matrix up to prefactor was fully fixed, you still have this Yangian behind. Now I'm running out of time somehow, but let me briefly say that this is a standard way of getting spectral parameter-dependent S matrices, because usually the Lie algebra generators, of course, do not depend on any spectral parameter, just in the special case of the central extension. So what you usually do is introducing extra sets of generators. Here I call them J1, with this relations to the original Lie algebra, J0, and which have a more complicated coproduct, which effectively leads to spectral parameter-dependent S matrix. This is a standard way how to obtain, say, rational R matrices. So, and the point is, okay, I don't want to talk about the technicalities. The point is that it's still, the Yangian is still here after some appropriate modifications. So you have this extra set of generators, and you need to do some modifications again to get a co-commutative Yangian. So in fact, this Yangian just works together with this coproduct. So yeah, so basically you need it in this picture, this coproduct I've shown before. So the full symmetry of this S matrix, this is basically this Yangian, and by twisted again I mean the introduction of the coproduct. So, okay, one question one could ask is, one can construct those R matrices of Yangians usually by completely algebraically, completely abstractly, which is difficult, but it should be possible in principle. Since we have here a strange Yangian, a twisted Yangian, so we thought that we might first study the simpler classical limit, and that's the basically now the paper I recently did with Niklas. So the algebraic structure on this classical level are Lie bialgebras. So what do I mean by a classical limit? I mean that I expand the R matrix. Now I talk about R matrix, not about S matrix. Doesn't matter, but this is kind of more natural here. So I expand it in some expansion parameter H bar. So I'm now interested in the so-called classical R matrix, little r, which arises at first order in H bar. So then all the properties of the quantum R matrix, capital R, like this intertwining condition, translate into this classical language as, for instance, that the difference between this coproduct and its opposite coproduct with the tensor factors interchanged is just the commutator of the Lie algebra generator with the R matrix. And because this is the most important quantity here on this classical level, we call this the co-bracket small delta R, small delta J. And likewise, the Yang-Baxter equation translates into the so-called classical Yang-Baxter equation. So, and if we have, and there's also compatibility between the this co-bracket and the ordinary Lie bracket. So if we have such structure, such Lie algebra with such classical R matrix satisfying those equations, we call this a quasi-triangular Lie bialgebra. And if we have that, the advantage is for those algebras there exist standard methods to construct this classical R matrix completely algebraically, not coming from any limit, no representation theory, but completely algebraic. So first of all, how we also did it is we need to identify what this H bar is. So usually for Yangians, you don't have much choice because there are no parameters except for the spectral parameter. But here we already have more parameters. So we need to say how do those parameters, for instance, the coupling constant G or the rapidity or momentum P, scale with H bar basically. So, and one natural choice is by just setting H bar as 1 over G, so meaning H bar to 0 means G to infinity, so we study the strong coupling limit basically, and the momentum scales just with H bar. So then we have to say how all the generators of the algebra behave. So to keep the momentum finite, so P scales with H bar, and this U I used before, this braiding element, was basically e to I P half, so I introduce a new generator D, which remains finite when I send G to infinity. And then those other central charges scale like that, so basically you only are left with a D, and the third central charge, this Hamiltonian, this energy eigenvalue C, basically also just depends on this D and this loop variable, this rapidity U. So, and in the sense of the loop algebra, so I was talking about the Yangian before. The Yangian is a kind of deformation of the loop algebra. So you would just say your generator, say you have now n levels, infinitely many levels, so you would just say level nth generator acts like the level 0 generator times u to the n. So since this u appears here, it means that this generator D is basically the same as a generator C, but one level shifted down. Okay, so that means effectively, instead of working with all the central charges P, K, and U, and C, you just need C and shift the levels appropriately. So what does this mean effectively? That instead of working with a central extension by 3 central elements, we just need to work, first of all, with SU2/2. So SU2/2 would just contain this extra central charge C. And then the other central charges, as I said, appear as different levels in the loop algebra. So the only thing is, this is now not the standard SU2/2, but a kind of deformation of that, because the central charge appears now in different places than you would have it for ordinary SU2/2 loop algebra. So one advantage of having only one central charge is that, so for algebraic constructions like R matrices or Casimirs, say, you need a non-degenerate bilinear form, which you don't have if you have central charges. You need something to pair them with, which are the outer automorphisms. So here we can include one more outer automorphism, which is basically leads to U2/2. But again, it's not just the standard U2/2. So in the standard U2/2, those automorphisms would act on the fermionic generators, just giving plus minus eigen values. And as usual in the loop algebra, the levels would just add up. So that's basically the standard commutation relations of the outer automorphism of U2/2 loop algebra. But you get an extra piece where the levels are shifted and the positive and negative roots are interchanged. So that's quite unusual. That's why we call it a deformed U2/2 loop algebra. And yeah, here again, those commutation relations of the positive and negative roots respectively, there also this level changing appears. So the advantage of having U2/2 is now that we have such non-degenerate bilinear form, which looks like that. It's just, if you couple, say, J and A with J and B, it's just the ordinary U2/2 killing form, and then the levels are paired in such a way that always the sum always adds up to -1. It's basically by using the residue as a invariant scalar product. So, and this pairing, so this is now important for the algebraic construction, this pairing couples the two subalgebras J plus and J minus, which are basically the, say, non-negative generators and the negative generators. They are basically coupled with this bilinear form. The only exceptions are those automorphism and the central charge. Due to those deformed commutation relations, they appear as shifted levels. But anyway, we have such pairing, which allows us to construct a classical R matrix completely algebraically. This is kind of a standard formula. So you just sum over all generators and always couple the positive level with this negative level via this bilinear pairing. This is just a standard formula you find in textbooks. And if you plug in this evaluation representation, Jn becomes u to the n j naught, then you would basically just end up with a quadratic Casimir on the tensor product. So the quadratic Casimir of u2/2, and which splits up into the Casimir of PSU2/2 and this automorphism central charge part. But due to this level shift here in this subalgebras, you get an extra twist term, which looks like that. So that's the only difference, say, to constructing the ordinary U2/2 loop algebra and its classical R matrix. So anyway, this classical R matrix gives the correct co-brackets, and it satisfies the abstract, completely abstract classical Yang-Baxter equation, which means that we have a quasi-triangular Lie bialgebra. And if we now plug in the fundamental representation, we reproduce the correct classical limit, which you get when you take the quantum S matrix and expand in the limit I've shown before. So yeah, what have we done? So again, the advantage is that we have a completely algebraic picture independent of representation theory. So if someone wants to compute another R matrix, another representation, he should basically find the same expression. So that's quite nice. And those important properties like Yang-Baxter are satisfied completely algebraically, abstractly. And another advantage is that one can do basically the same in other classical limits. For instance, also in the weak coupling regime, where we basically scale a G like H bar. So there we find the same structure, which is maybe not that surprising because this U2/2 or PSU2/2 was found both on string and gauge side. So then we need to scale this rapidity with a different, in a different way. And what we also found is that at least some of those extra automorphisms, which were previously not included, are also symmetries of the full quantum S matrix. Yeah, and from this, what we've established, one can go on and construct maybe the full Yangian as an abstract quantum group, including maybe the R matrix algebraically, which should be automatically crossing invariant, because in quantum groups there exist such equations which lead to crossing automatically, which might lead to some new input on the dressing factor, or not. I don't know for the moment, but at least it should be somehow crossing invariant. And yeah, what would also be interesting to go one level up and study the relation to the full Yangian of PSU 2,2/4. That's it. Thank you. Well, there are some ideas how it might work, or already some proposals. For instance, in Niklas' last talk in Paris, like you can split up the action of the Yangian generators of PSU 2,2/4 into the PSU 2/2 part, and then some remaining part, and somehow see that the structure should come out. So. The remaining part decouples, yeah, and decouples.
So in the end, you have just PSU 2/2, and there is no relation to PSU 2,2/4.
Yeah, but so you can act with, say, the Yangian generators on the full spin chain, and
you would have to have the finite J spin chain, and you don't have it.
Yeah, okay, you don't have it, so you.
Relation is just the asymptotic beta ansatz. And if, I mean, you believe that.
The asymptotic beta ansatz is J equal to infinity. J equal to infinity, you have only
has the word asymptotic. So That explains it.
Yeah. So why do you expect the relation? Any relation?
Okay, maybe continue. Some maybe one more question. Probably.
No.